Welcome back. So today we're just going to continue talking about convergent sequences, but this time I'll actually show you how to prove some of them. Okay, so my first question I want us to look at was prove the sequence of just 4 over and over and over again is convergent. So you probably, if you've been watching my videos, you probably know my style by now. I like to start with something that seems fairly simple so we can at least get the bare bones down. And then go from there. So let's start by saying, so I always have these like little ways to make things easier for myself. I'm going to set this equal to an and the naturals. I know right now it doesn't really matter because for any natural number, an is 4. But this is a nice trick for the future, so you don't have to like write out the whole equation if there's equation every time. Okay, so proof. All right, so let's recall what the definition is. Okay, for all epsilon in the positive reals, or sometimes how people will write it is they'll say for all epsilon greater than 0. So remember, epsilon cannot equal 0, or else a lot of sequences would not be convergent at all because they don't actually end up equaling the limit forever and always. So for all epsilon greater than 0, there exists an n in the naturals such that for all n greater than or equal to capital N, well, these n's are in the naturals, a sub n minus L less than epsilon. Okay, so that's our definition in general. All right, so let's start our proof. Okay, so we need for any epsilon. So why don't we start by just choosing some epsilon? Choose epsilon greater than 0. Boom, okay? All right, so now I'm going to immediately go over to scratch. And so this is typically when I start. So maybe in your head you do a limit or something. Remember, we're not writing like lim an stuff. No. Okay, the only limit we're talking about is this L. That's the only one. Okay, so maybe you go into scratch. Maybe you try to think about what the L should be. Okay, but we do know here that our limit is 4. So set L equal to 4. So this is just me claiming that our limit is 4. Okay. So now I need to know which n to choose, which capital N. So let's look at scratch. So remember, the deal with scratch is we get to assume what we want. Okay. So what is it that we want? We want an minus 4 to be less than epsilon for any epsilon. Okay. Okay, so, well, any an, so this is usually when I plug in the formula for an, but our formula is just 4. So 4 minus 4 less than epsilon. Oh, cool. Okay, well, that's 0. So what do we have to do to make 0 less than epsilon? Absolutely nothing, because 0 is always bigger than, epsilon is always bigger than epsilon by definition. Okay, cool. All right, so then we get to just choose any n in the natural numbers. Then for all n greater than or equal to n, we have a sub n minus, so here's another thing that I really like. I really like starting with this. Even if you know what an is, even if you know what L is, a lot of students get ahead of themselves and forget to show all their work, and then all of a sudden they just have like, I don't know, just like too much, you're too far ahead, right? But you haven't shown the reader all your work. Okay, so I like to always start with this so that I know for sure that I'm saying everything that I need. And so now in this next one, now I can jump to plugging in what those two things are. Okay, so that equals 0. Well, that's always less than epsilon by our definition. So I would say by assumption, therefore, our sequence 4 n in the naturals converges to 4. Okay, so then if you were just going to write this short of a snippet at the end, you would need to put in what the definition is of convergent sequences above, or else you would have to write for all epsilon greater than 0, there exists an n in the naturals such that for all n bigger than or equal to capital N, to value an, yeah, because we did define it as an above. An minus 4 is less than epsilon. And then you would say this bit here. Okay? But if you did write your definition somewhere of what a convergent sequence is, then I think you would be good. Okay? Alright. Alright, so now let's talk about what the outline is. So outline, the very first thing we do is fix arbitrary epsilon greater than 0. Okay? So, boop, figure out who L is. Okay? Then scratch work. What we do is we look at an minus L less than epsilon. Okay? So we look at this and we manipulate it until we're able to figure out some function for n. So like n, some inequality with n and epsilon in it. So little n has to somehow work with epsilon. So you manipulate this until you get something that looks kind of like this. Okay, so you have little n is bigger than, and then this m sub epsilon is a number that possibly depends on epsilon. So in our situation, we did not have that, right? So in our situation, it actually simplified pretty quickly. But what we could have done is we could have kept a sub n, yeah, never mind, get rid of that. So in our situation, it didn't depend on epsilon. We just needed any n bigger than 0, any natural number, okay? But in the future, you might have like that maybe n needs to be bigger than 1 over epsilon, okay? And now that's when you're going to chime in and use a p on that, okay? All right, so back to proof. Use AP. And if you haven't seen, if you don't know what AP is, or Archimedean property, go back to my previous video on it. To pick n in naturals such that this weird m epsilon thing is less than capital N. Next, so a lot of these things we kind of glazed over because we didn't need to show them in our last proof, okay? Do work to show absolute value of a capital N minus L is less than epsilon. Okay, cool. 6, now you want to show for any natural number bigger than or equal to capital N that a sub n, little n, minus L is less than or equal to a sub capital N minus L. Okay, so why is that? Well, secretly that's because this is less than epsilon. We've already shown that. So then boom, we're done. Okay, so now 7, use 5 and 6 to show that a sub n minus L is less than epsilon for all n bigger than or equal to capital N, once again. And then 8, conclude the proof saying this is true for any epsilon. Okay, so something that sometimes people get stuck on is they will be manipulating to figure out this up here, so their m epsilon less than n, and maybe they'll get too big too fast, okay? So sometimes that happens, and then the n that you pick is, or the m sub epsilon that you pick is not very helpful, okay? Sometimes people have gotten themselves into a little tizzy where they showed that like epsilon had to be bigger than something, Well, the only thing that we're guaranteed with is that epsilon is bigger than 0. Okay, or a negative number, so the same. You can never get yourself into something where it says epsilon has to be bigger than 1/8. Because remember, it has to be for all epsilon. Okay, no matter how small. All right? Okay, so that's the outline of one of these proofs. I know that's a lot. Okay, so let's do one. Show 1 over n in the naturals convergent sequence. All right, so I'm going to let 1 over n equal an. Just make my life a little bit easier. Okay. All right, so let's do my proof. Step 1, choose epsilon greater than 0. Boom, roasted. Step 2, what is going to be my L? Okay. Well, L is going to be 0. Scratch. All right, what do I want? So I want a sub n minus 0 to be less than epsilon. Okay. So that just means absolute value of a sub n less than epsilon. Okay, well, who is a sub n? That's just 1 over n. Well, that's always going to be positive because we're only n's are from the naturals. So I want this. So remember, I want to write this as little n bigger than something that possibly has to do with epsilon. So both epsilon and n are both bigger than 0, so I can divide both sides by them without worrying about dividing by 0 or without worrying about having to flip the inequalities. I'm multiplying n, but I'm dividing epsilon. Okay, so we have 1 over epsilon needs to be less than n. Okay. So now I found my secret sauce here. Now I'm going to use AP. By AP, choose n in the naturals such that 1 over epsilon is less than n. And you can shove in there why you're allowed to use AP. That would probably be very good technique. Not so sure it's necessary, but that since epsilon is a real non-zero number, 1 over epsilon is a real number. Okay? So we can use AP. All right, awesome. Now I want to use with my capital N. So a sub capital N minus 0, or minus L, remember I said I should always do that, is 1 over capital N minus 0, which is absolute value of 1 over n. Okay, well I know that that's just 1 over n. Well, that's less than epsilon. So the way that you can think about this is you can say, all right, well, if I make my denominator smaller, I'm going to make my whole fraction bigger. Okay, so what I'm really saying is this is less than or equal to 1 over epsilon, which is epsilon. Okay? Now I want any n that's bigger than capital N. Consider n in the naturals such that n is bigger than or equal to capital N. So me talking in such generality, this is going to prove it for any n bigger than or equal to capital N. All right, so once again, I have a sub little n minus L. Now I'm going to cut to the chase because we've done that so many times. Okay, so it's 1 over n. Well, I know that capital N is less than or equal to it. So if I make my denominator smaller, I make my whole thing bigger. Or equal to, if they're the same. So I have 1 over capital N. Well, I just showed up here that that's less than epsilon. So now I hope you see why I like to write it like that first. Okay? So let's pretend I already said what the definition. Well, let's just write it out. Yeah, let's just write it out. All right, therefore, for all epsilon greater than 0, there exists a capital N in the naturals, such that for all little n bigger than or equal to capital N, a sub n minus L minus 0, or we could even say 1 over n minus 0 is less than epsilon. So 1 over n in the naturals converges to 0. Okay? You always need to end it with what it converges to. Okay? All right, that's it.